quantities. And we reintroduced what into chemistry. Was one of the things I say is if you get this down, you pretty much have 90% of general chemistry down. What did the problems we were doing last time look like? Or we ended with last time? That we did at the beginning of the semester. Unit conversions, right? So these are basically just unit conversions and using chemical quantities to do unit conversions, right? So these are heavily relying on unit conversions and just using chemical quantities to do stuff like the molecular formula, balanced chemical reactions we'll get into using those. And we talked about two things. Specifically, we talked about the idea of the mole. And so what was a mole besides an animal? It is a standardized unit. And what does that unit represent? Standard, I can't spell that. It represents a number of things, right? A standardized unit for a number of things, right? So we're trying to build this idea that the mole is like a counting device. It's not some weird nebulous thing. It's just when we say a mole, we want to know that that means exactly a specific number of things, right? The same way when we say we have a dozen things, that means that we have 12 of them, right? Or a couple, that means we have 2, right? And when we have a mole, we have how many of them? How many things? Yep, 6.022 times 10 to the 23, right? Does anyone remember what this number was called? Yeah, this was Avogadro's number, and we used it, and it was symbolic we used. Na was Avogadro's number, right? And this just represents the number of things per 1 mole of that thing, right? So if we have a mole of stars, that means we have 6.022 times 10 to the 23 stars. And the reason we do this is because in chemistry we're dealing with things that are very what? Small, right? Which means the number of them is very large, right? If we're looking at a glass of water, you have, half a mole, which is like 3.022 times 10 to the 23 water molecules in that glass of water, right? It's a very large number of things, which is why Avogadro's number is so large. But the things we're dealing with tend to be very, very small, which is why it's easier to, deal with the reaction happening 1 mole times rather than 6.022 times 10 to the 23 times, right? And so this gave us a conversion between moles and things. And we also talked about another chemical quantity. Does anyone remember what that was? The molar mass, right? This was the molar mass. And what does the molar mass represent? It is. It's given to us on the periodic table by the atomic mass. And those units are AMU. And what else are those units? And the units also tell us the definition of what the molar mass is. What are the units of molar mass? Grams per what? Grams per mole, right? So the molar mass tells us how many grams is 1 mole of that substance, right? So before I said, if you have a cup of water that's like half a mole of water molecules, it means we have 3.011 times 10 to the 23 water molecules in there. The molar mass just says, well, if I have, 23, or let's say if we have 44.95 grams of scandium, that means that I have 1 mole, or I know I have 6.022 times 10 to the 23 atoms of that element, right? And so this was given to us by the periodic table, Right, if we had our icon, the atomic number is up here, the element, and then the atomic mass was given right below that element on most periodic tables. And if you had a molecule instead of an atom, how do you find the atomic mass of a molecule instead of an atom? You add what? Like if you had H2O, what are you adding together? Yeah, you're adding the molar mass of all the elements that are in the molecule, right? So the molar mass of a molecule is just given by the sum of the molar mass of each of the elements. All right, so if we have the molar mass, and I usually use MM to abbreviate that, of a molecule is given, I realize I'm on the wrong PowerPoint, given by the sum of the molar mass of its elements. So for example, if we have H2O, the molar mass is equal to the molar mass of oxygen plus 2 times the molar mass of hydrogen, right? Because we have 2 hydrogens in this molecule and 1 oxygen. Right, so we want to be comfortable calculating the molar mass of any molecule that we're given, right? We built up these ideas of molecules. You know, chemical formulas are a representation of that molecule. It tells us how many atoms of each type we have in there. If we know how many atoms of each type are in the molecule, then we can get the molar mass of that molecule. And so then we started talking about, well, we can use these chemical quantities as conversions to go between 3 different things in this case, right, for single molecules, or atoms, elements and atoms of a substance. We could go between mass, moles, and number of things, right? And the reason I put number of things is because we can be asking about the number of ions, number of molecules, or the number of atoms, for example. And so we could go between each of these using these chemical quantities. And so how do we go between grams and moles? What did we use? Avogadro's number or the molar mass? The molar mass. And going between moles and number of things, what did we use? Avogadro's number, right? That tells us if we have a certain number of moles, we can then calculate how many atoms or molecules we have of that substance. And how do we know how to use the molar mass or Avogadro's number, right? We're going in one direction or another. That tells us how we're going to use that quantity, right? So that means that, are we multiplying or dividing by the molar mass? So usually the unit that we're going to needs to be where in our conversion? In the numerator, right? And so if the units for the molar mass, remember this bracket here means units, were grams per mole. And you can write mole, M-O-L-E, or M-O-L. Both are acceptable. And we want to go from grams to mole in the right-hand direction. How do you use the molar mass? We multiply by the inverse or we divide by it. Why? Because we know that moles needs to be in the numerator, right? Which means that we have to take the units, our grams per mole, we need moles in the numerator. How do we do that? We just invert that number, right? So when we're going in this direction, we do 1 times 1 over the molar mass, and that gets us to moles. And that means that in the other direction, what do? We just multiply by the molar mass. That's correct. And we're just looking at where the units are and where we need them to be, based off the dimensions or the units of these numbers themselves. And so then if we're going from moles to number of things, how do we use Avogadro's number? The units for Avogadro's number were things per mole. So how do we use Avogadro's number if we want to end, if we start with moles and we want to end with number of things? Yep, we multiply by Avogadro's number when we're going in this direction, and then we divide when we're going in the opposite direction. Right, so we're kind of building these flow charts. How do we go from units of one thing, so the mass, for example, to the numbers of those things? These flow charts are kind of useful to keep in mind because when we get to chemical reactions, you might start with grams of a reactant, you might end with grams of a product. Well, how do we do that? Well, we have to build a flow chart like this to make sure we're going and canceling out the appropriate units. All right, so that's kind of where we ended off last time. So any questions on that? All right, so let's go over an example, maybe one that we didn't finish last time. And so again, this was related to your magnesium oxide lab. Today's lab will be a little bit less calculation intensive, more just lab time intensive. All right, so this is the example that we left with last time. How many magnesium atoms are present in 5 grams of magnesium, right? So all we did was built the flow chart last time. See if you can actually go through and calculate the conversion, right? So the steps, when we put them out like this, they seem relatively simple, but we have to understand, that this is a single atom. How do we get the molar mass of that atom? And then how do we relate that to the number of atoms? Right, and so in this case, your Avogadro number, the things that you're looking for is just going to be the number of atoms. All right, so what do we not have that's given to us that we need to solve for this problem? We need the molar mass of what? Molar mass of magnesium. And what is the molar mass of magnesium? 24.345 grams per mole, 0.5 grams per mole of magnesium, right? It's important that we use grams magnesium and moles magnesium, not for this problem necessarily, but in general, once these problems start to get more complicated, we'll be using different molar masses, right? So they're both going to be units of grams, but we need to know what units of grams we're talking about. Are we talking about grams of one molecule or an atom or so on and so forth, right? So it's just good habit to start writing it this way. And so we start with 5.0 grams of magnesium. And then how do we use the molar mass? We divide by it, right? Which is 1 over the molar mass of magnesium. Another way we write that is 1 mole magnesium per 24.305 grams of magnesium. 1 mole magnesium, 24.305 grams of magnesium. So what happens to our grams? Go ahead. You don't have to. You can do it however way makes the most sense for you. I'm not, as long as you get to the kind of right change of units in the end, I'm okay with that. I do it this way just because it's easiest to see how the units are going to cancel out. Right? You don't have to write everything that you have up there. I'm just doing that to show you where I get the numbers from. And especially when you're dealing with different masses and stuff, if you don't write the element or the molecule that you're looking at the molar mass of, it'll start to get a little confusing. Okay, so what happens to the units of grams? Grams magnesium cancels out, so we're left in units of moles now. And then we use Avogadro's number to end with the number of atoms. And so what do? Multiply by Avogadro's number, which is 6.02 times 10 to the 23 atoms of magnesium per 1 mole of magnesium. Right? So when anything has units or dimensions that are in a fractional form, we can always write it like this. So what happens to the moles of magnesium now? They cancel out, and we're just left with atoms of magnesium, which is exactly what we're solving for. And if I said there's 5 grams of magnesium, right? It seems like a small amount in terms of mass, but in terms of the number of atoms, what do you think that should be, small or large? large, right? Because an atom is smaller than the eye, visible light can even interact with. So the number of atoms in 5 grams, which may be like a teaspoon, should be a very, very large number, right? So we'll try and use some of our chemical intuition when we're looking at these answers to see if they make sense, right? If we ended up with a really small number here, that means we probably flipped Avogadro's number in here, right? If I got like something like 10 to the minus 22, I'd probably flip something around. And so when I plug this all in, get 5 times 6.022 times 10 x to the y, 23, divided by 24.305. Okay, it didn't give it to me in scientific notation. Was it 1.24? And what was the exponent for this? My calculator didn't give me in scientific notation, so I'm not going to count all the. So divided by 24? Okay. Times 10 to the, should probably be the, 24. Should probably go the other way, I think, right? Because we have less than 5 grams. Yeah, 1 mole. Yeah, 1 mole is 24 grams, so we have about 1/5 of that, which means that we should have about 5 times 6.022 times 10 to the 23. So I'm guessing, is it 22? Is that what you guys got? 23? Okay, it stays 23. Let's just do that in 5 times 6.022. Okay, yeah, should stay. Yep. Divided by 24.305. Yeah, so it should stay the same at 23. Yep. Atoms of magnesium. So initially I put it all in my calculator. I don't know why I did that. It was easier just to do it in terms of scientific notation and then just leave the exponent to adjust at the end. Okay, and so a lot of these ones, especially if it's just a single atom, are going to be relatively straightforward. The process of, depending on what you're given, will just tell you which way you have to go and how you use these chemical quantities to go between the different units. Okay, any questions on this one? All right, so see if you can do the same thing now with 25 grams of hydrogen chloride. It says how many molecules, which means that Avogadro's number will be 6.022 times 10 to the 23 molecules HCl per 1 mole of HCl. Right, so that's how Avogadro's numbers changes depending on what thing we're talking about. It's always going to be, get your flow chart on where you're going to start and where you're going to end with. So what are you going to be starting with here? What units? 25.0 grams of HCl, right? And you're asked to find the number of hydrochloric acid or hydrogen chloride molecules. So what do you need to convert to before you get to the number of HCl molecules? Moles of hydrogen chloride, right? You need to go to moles first, and this is going to be a common theme in everything we're doing is when you're looking at, converting from mass of one element to another, whether it's in molecules or in chemical reactions, you always go to what I say is like the universe of the moles, right? Because that's what allows you to go between these things, because that gives you direct comparisons of amounts. Mass, you can't compare directly because different atoms weigh different amounts. Moles tell us the actual number ratio of things. And so how do we go from grams to moles? The molar mass, we're going to need to find the molar mass of hydrochloric acid. Then moles to gram or number, we use what? Avogadro's number, that's right. And so what is the molar mass of hydrochloric acid? It was 36 point what? 46 grams hydrochloric acid per mole HCl, and that's equal to 16.00 grams per mole oxygen plus 2 times 1.01 gram per mole hydrogen, right? We just took the sum. Huh? Oh, wait, yeah, we're doing hydrochloric acid. I was still in water in my head. So it's chlorine. What's the molar mass of chlorine? 35 point what? 45 grams per mole chlorine, and then 1.01 grams hydrogen per 1 mole hydrogen. All right, that's how we get that number on the left there. We add the molar mass of each of the elements in our molecule. And so we go through the calculations, 25.0 grams HCl. We use the molar mass, and how do we use it? We're going to divide by it, right? So it'll be 36.45 grams, 36.46 grams HCl per 1 mole HCl, which is then cancels out what units? Grams. So we're left with units of moles. We're in the universe of moles now. Now we can go to the number of atoms. And so atoms, we use Avogadro's number, and we multiply because we want what to be in the numerator? Molecules. Let's see if I can write this small enough. HCl over 1 mole HCl. Those cancel out now, and then we just plug that into our calculator. I'll just multiply all the coefficients, which is 25 times 6.022 divided by 36.46. So that gives me 4.13 times 10 to the 23 molecules of hydrochloric acid. Did everyone get something similar? All right, so this is going in one direction. You can also ask the other direction. If I start with 4.13 times 10 to the 23 molecules of hydrochloric acid, how many grams do I have? Right, so we've only gone in one direction. We can also go in the other direction. So when I give you guys a problem set, I'll probably do more examples of that on there as well, right? So one thing to know, especially in chemistry, if you know how to do things one way, it's always probably a good idea to learn how to do it in the reverse direction as well. All right, any questions on that? No? All right. And so now we'll talk about, well, now we have molar mass of molecules. Well, how can that give us a relationship between the specific elements within that molecule to the amount of the molecule we have itself, right? So this is honestly how chemists used to do everything back in the day. You know, we had an idea of valence, you know, how many elements an element can bond, just based off of the amount that we would expect within a certain compound, right? So you can get the chemical formula just by measuring different masses of things. And so the subscripts in the chemical formula indicate the number of atoms, which we know very well. And so for this molecule of aspirin here, how many carbon atoms do we have? We have 9 carbon atoms. How many hydrogens? 8 hydrogen. And how many oxygens? 4 oxygen atoms. Right, so we can know number ratios. Well, if we have one molecule of aspirin, that means we have 9 carbons present in this single molecule, right? And so we can take that, and then we can expand it. Well, now if I have a mole of aspirin, right, that's now a macroscopic quantity, something that I can weigh and measure. I should know how many moles of carbon I have, how many moles of hydrogen, and how many moles of oxygen. So I see some people are still writing, so I'll give you guys a second to finish writing before I go on. And so this is going to allow us to then go between moles of atoms within a molecule to moles of the molecule itself. But like I said before, you're generally going to have to convert things into units of moles before you can transfer them. And it's because we're going to introduce a new conversion in the next slide after this one. Right, so if we have 1 mole of aspirin, right, so we have 1 mole C8 or C9 H8O4. How many moles of carbon do we have? 9 moles carbon. How many moles of hydrogen do we have? 8 moles of hydrogen, and then 4 moles of oxygen. Right, so the subscripts not only tell us the number of elements within a single molecule, they also tell us the moles of that element within a mole of that molecule. Right, so the moles are what we're allowed to convert between. And this is again why if we just measure 25 grams of aspirin, we don't say, well, 1/9 of that mass is because of carbon. Even though we have a 9-to-1 ratio of carbon to aspirin, we can't say that because carbon atoms weigh different than hydrogen and oxygen atoms. Right? That's why we have to use moles when we're going between these. They give us direct ratios between the number of atoms and the number of molecules, where masses are unequal between different atoms. Right? So carbon contributes differently to the total mass than hydrogen does. And so if we're given a molecule, just the chemical formula gives us conversion factors for each of the elements in 1 mole of that substance, which means that we have 9 moles of carbon for every 1 mole of aspirin, 8 moles of hydrogen for every 1 mole of aspirin, and 4 moles of oxygen for every 1 mole of aspirin. So this is exactly what we wrote on the previous slide, except now we're looking at it in terms of a conversion factor, right? Which means if I measure the mass of aspirin, I convert that to moles of aspirin. Now I can use this to go between moles of aspirin and moles of oxygen, and then I could get the mass contribution of oxygen to the total mass of all the aspirin that I have there. Because for each of these conversion factors, they all come from a conversion equality, right? This tells us that 9 moles of carbon equals 1 mole aspirin if we're looking at this compound. Right? We have this conversion factor, and then we also have what other conversion factor based off of this equality? You have the inverse, right? So you could be given, well, I know that I have percent by mass carbon in my substance. What is the mass of aspirin I can make from that? Right, this gives us this conversion factor, and it also gives us the inverse, which is 1 mole aspirin over 9 moles of carbon. Because you get 2 conversion factors for every conversion equality. How do you know which one to use, which direction you're going? Vanessa?
So these conversion factors help us kind of figure out, like when you said, like in the previous example, like to separate each of the elements?
Yeah, it's so, right, so you're like, wow, why would I want to do this? Well, if you're just looking at a single sample, maybe it's not that useful to look at, the carbon within how much aspirin you have. But when you start looking at chemical reactions, if you say, well, I know I have this much carbon on this side of the reaction, how much product can I actually make based off of the amount that I have? Right, so that's why this is useful, is because when you convert things to moles, then it'll allow you to convert it to, potentially how much molecules of something else you can make. But we're still kind of building up to the idea for chemical reactions. Or for example, if you did some other measurement, maybe more sophisticated thing, and you could only measure the amount of carbon you have in your compound. If you know the chemical formula, then you could say, well, now I know I have this much of all of the drug that I'm synthesizing or something like that. But yeah, we're kind of separating here, right? We're separating the moles of aspirin, or the molecule itself, from moles of its constituent elements, or what elements are inside that molecule. And so, for example, in your guys' lab last week, that's what you guys did. When you burn the magnesium, right, you gained a certain amount of mass. You know that mass only comes in oxygen, right? Because you know the chemical formula for magnesium oxide, that means that you can determine what percent of all the magnesium you had actually reacted into magnesium oxide. But you only measure the mass of oxygen. You don't know the mass of magnesium oxide. So that's why it can be useful to separate these compounds. All right. And so if we have these two drugs, we have Tylenol. Apparently you're not supposed to take that anymore. And a zinc dietary supplement. I'm just kidding, Tylenol's fine. And the zinc supplement. See if you can figure out the moles of carbon atoms based off of 1 mole of each of the following drugs. So what two things are we converting between here? So I'll give you guys a hint. These problems are actually simpler than the ones that we just did. You probably don't even have to do any math for these ones. All right, we're looking to find the number of moles of carbon atoms, right, in 1 mole of each of the molecules, right? So we're going between what two units? Moles to moles, right, which is going to be one of our simplest. And we're going between specifically how many moles? What are we starting with?
8 moles of carbon.
Or we know that's going to be our conversion between them, right? But we're starting with 1 mole of each molecule, right? So we're starting with 1 mole of molecule. So in that case, this is 1 mole C8H9 NO2. And in this case, we're starting with 1 mole zinc C2H3 O2, right? So we just need to find the conversion that goes between moles of the molecule in moles of the molecule. What gives us that conversion? Sorry, the moles of the carbon atoms. Moles of the molecule to moles of the carbon atom. We want to end with moles carbon. All right, what gives us that conversion factor? Sam?
Would it be 1 mole of carbon over 1 mole of Tylenol?
So we wouldn't necessarily have 1 mole of carbon because we have how many molecule atoms of carbon per?
What, 8?
Yeah, we have 8 moles of carbon per 1 mole of Tylenol, right? So, because it's the chemical formula that gives us the molar conversion, right? So for this first one, we have, for every 8 moles of carbon, we have 1 mole of Tylenol. All right, and where did I get that? How did I get 8 moles for every 1 mole of Tylenol? I got that from the chemical formula, right? The subscript there is what tells me, because that tells me I have 8 carbon atoms per molecule, right? If I multiply that by 6.022 times 10 to the 23, that means I have 8 times 6.022 times 10 to the 23 carbon atoms per 6.022 times 10 to the 23 molecules of Tylenol. Another way of saying that is I have 8 moles of carbon per 1 mole of the molecule. Right, so again, the chemical formula gives you the molar ratio. And so that's what we'll call this conversion between moles of one substance to moles of another. And that's either gonna be moles of atoms to moles of molecules, or moles of molecules to other moles of molecules is what we're gonna talk about shortly. So what happens to the moles of Tylenol in this case? They cancel out, right? These two cancel out, which means that I just have 8 moles of carbon, right? So we don't really have to do any calculating here, right? If I asked you then to find the number of carbon atoms based off of this, then you would have to use Avogadro's number to get the number of carbon atoms. And what about for zinc? What's our molar ratio going to be for the zinc dietary supplement?
4 moles of carbon.
Yeah, it's going to be 4 moles of carbon. So why is it 4 instead of 2?
Is it 2 subscripts?
Yeah, we have a 2 subscript outside the parentheses, which means what do we do to all of the subscripts in here? We multiply them by 2 to get the total number of atoms there. Right, so this means that we're going to have 4 moles of carbon for every 1 mole of this dietary supplement. So that just gives us 4 moles of carbon. Right, so the takeaway here is just that the chemical formula gives us the molar ratio that allows us to go between moles of an atom to moles of the substance, or the molecule in this case. All right, any questions on that? All right, so again, we're looking at this in the same way we'd say, well, each molecule of this has 4 carbon atoms. That means that each mole of that molecule has 4 moles of that carbon atom.
So you never have to really do math, you just.
Well, in this case, right, we're only doing the simple step going between moles of the molecule to moles of the atom. If we're going from grams of the molecule to grams of the atom, then there's going to be more conversions that you would have to do. All right, so we have, in this case, this is another simple one, so we'll skip this one. Where is the... All right, I'll just change this problem. So how many carbon atoms, or let's look at something even more complicated. What is the mass of carbon present in 1.5 grams of aspirin? So now we have to build a chart. Where are we going? Where are we starting? We're starting from grams of aspirin, and we need to go to grams of carbon. Grams of aspirin. So, all right, so what's your flow chart here? You're starting from grams of what? Aspirin. And what do you need to convert that to?
Is it moles or grams?
You need to convert it to grams of carbon eventually, but what do you first have to convert it to before you can get to? You need to go to moles of aspirin first, right? Because moles of aspirin tells us the numerical ratios of everything, right? That tells us the actual numbers of things. That's why we have to go to moles first. So we go to moles of aspirin, H8O4. And then we can use moles of aspirin to go to what? Moles of carbon, right? We go from moles of aspirin to moles of carbon. Doing what? Well, using the molar ratios that we just talked about. And then we can use moles of carbon to go to what? Mass of carbon. Right? And so now let's, before I let you guys think about it again, what are you going to use to go from grams of aspirin to moles of aspirin? What chemical quantity? The molar mass, right? The molar mass of that molecule. So that's going to be the molar mass of C9H8O4. Then once you go from then you need to go from moles of aspirin to moles of carbon. That's what you're going to use the molar ratio for, which is what we just talked about. And then going from moles of carbon to grams of carbon, what are you going to use? You're going to use the molar mass of carbon. Right, so there's 3 different conversion steps we have to do here. All right, so I'll let you guys think about it. Think about how you're going to use those things. Are you going to multiply, divide by them? How are you going to get the units to work out these cases? From grams carbon. When we write this flow chart, that means that we're given this quantity, and then we have to fill in all the conversion factors to end at one point with units of moles of aspirin, then use another conversion factor to end with units of moles of carbon, and another conversion factor to end with, finally, grams of carbon. All right, so we're starting off with how many grams of aspirin? 1.50 C9H8O4, right? And we need to convert that using the molar mass of aspirin. So what's the molar mass of aspirin? Yeah, 180.16, right? And are we going to be multiplying or dividing that? Dividing. So where should 180 go? In the numerator or the denominator? The denominator. And how do we know that? Well, the only way the units of grams are going to cancel out, and we end with units of moles, is if we do things this way. H8O4 per 1 mole C9H8O4, right? So now we can check just to make sure we're on the right track, right? So we're just following this flow chart sequentially. We use the molar mass, and we see that grams cancels out with grams, right? Which means now we're left with units of moles, which is where we should be after the first conversion step. All right, so we're left with units of moles. Then we're going to do another conversion to get this into moles of carbon. And so we're going to use the molar ratio for that. So what is the molar ratio? There should be 9 moles of carbon for every how many moles of aspirin? 1, right? It's a 1:9 ratio. How do you know that? The chemical formula says that we have 9 atoms of carbon for every 1 molecule of aspirin. And we want moles of aspirin to do what? We're going to end with units of what after this next conversion? After, at the very end, we want to end with grams of carbon. Before we get to grams of carbon, what units are we going to? Moles of carbon, right? So that means that in our molar ratio, the moles of aspirin should go in the denominator because that's how they're going to cancel out. That's how those units are going to cancel out. So we have 1 mole C9H8O4 per 9 moles of carbon. We see moles of aspirin cancels out, and we're left with units of moles of carbon, which is where we should be at this point in our unit conversion. And so that means we only have 1 more conversion to do. And how do we go from moles of carbon to then grams of carbon? How do we go between moles and grams in general of anything? Multiply by what? The molar mass, right? The molecular weight or the molar mass, right? So we're just going to be using the molar mass again. And what units do we want to cancel out? We want 1 mole of carbon to cancel out, which means that we just multiply by the molar mass, which is what, 12.01? 12.01 grams of carbon. And now we see that moles of carbon cancels out, and we're left with grams of carbon, which is what our final answer should be. All right, so the whole purpose of this multiple step unit conversion is first we have to get things into units of moles. Why? Because that gives us a numerical comparison between the amounts of things, right? We can't use mass because masses aren't equal, right? So that allows us to use molar ratios to go between moles of carbon in this case and moles of the entire molecule. So that gives us, if we plug everything in, and so in this question, we didn't have to use Avogadro's number at all, right? Because Avogadro's number tells us the number of things. In general, unless we're asking for the number of things or given the number of things, you're not going to have to use Avogadro's number. That's only when you're asking for the number of molecules, atoms, ions, or whatever. So we get 1.5 times 9 times 12.01 divided by 180.6 divided by 1. So that gives me 0.8, I'm going to put 900 grams of carbon. And so just looking at this mass, how much carbon we have, that's roughly more, that's like 60% of the total mass in the molecule, right? Because we have about, or in the amount that we have, right? We have 1.5 grams, and this is almost a whole gram is due to carbon. Why is that? Because there's a lot of carbon in the molecule, and it weighs more than hydrogen, right? So that's why we have a lot of hydrogen, but it doesn't weigh as much as carbon atoms do. Right?
Did you get the molar mass of aspirin?
So the molar mass of aspirin, I'll go back to the slide in a second. Molar mass of C9H8O4 is equal to 9 times the molar mass of carbon, because there's 9 carbon atoms, plus 8 times the molar mass of hydrogen, because there's 8 hydrogen atoms, plus 4 times the molar mass of oxygen. And so 9 times 12.01?
Yeah.
0.01 grams per mole plus 8 times 1.01 grams per mole plus 4 times 16.00 grams per mole. Is that what you did? Okay, I was gonna say, do I need to go through and calculate, or is...
To the power of those numbers on X.
Oh, yeah. So the power of numbers will come in later when we talk about equilibrium, but right now we just multiply that. Yep. So that's why aspirin is kind of annoying, right? That's why I just looked it up on Google. I didn't feel like plugging all that into my calculator. Right, there's a lot of different elements in there to calculate the total molar mass of that compound. But how does Google do it? Well, Google did the same thing that I did here. Okay. Any questions, Simon?
I know this is like way back, but would that be 3 sig figs?
Yeah, so you'd only use 3 sig figs here. Why? Because there's 3 sig figs given to you, no problem. Generally, the molar mass is dependent on the periodic table you have, so sig figs are only going to be based off the numbers you're given in these problems.
So I was asking because in my calculator I got, it only showed me 0.9.
Mm-hmm.
So if I didn't add those 2 sig figs, would I be like wrong technically?
Well, you could just add the 2 sig. I mean, you wouldn't be wrong technically. You would be less accurate, but right now I'm not focusing too much on sig figs for this. But technically, yeah, this would be 3 sig figs. So if your calculator only gave you 0.9, you would just have to put 2 zeros. Or if it only gave you 0.8, you would just add whatever sig figs you need for that number. How do you do that? If you're only given 1 digit, just add zeros after that digit. Mm-hmm. Or underline a digit. All right. Like I said, so this one is a little more complicated, right? So this is actually a lot of work, but in terms of if we just write out our sequential unit conversion steps like this, it simplifies it a lot. Okay. And so generally, if you're given a compound or a molecule, right, you can use this as the same flow chart that we have used, or we're kind of been building up. It's just all nicely put together. If you were to put something on a note card for an exam, I would say this would be something good to put on there. Why? Because if you're given something, right, and you know what you're given and you're asked to solve for something else, you can just follow this flow chart, and that will always tell you how you're going to get to whatever it is you're given, right? So if you're given the grams of an element, and I ask you to find the grams of a compound, the easiest way to do that is to go to molar. The moles of the element to the moles of the compound to the grams of that compound, right? Or vice versa, right? So what we just did is we were given the grams of the compound. We went to the moles of that compound, moles of aspirin. Then we went to moles of carbon, right? And then we went to grams of carbon from there, right? And how do you get between each of them? Well, it depends what two things you're going between, right? So if we want to go to the number of atoms, we would have to use Avogadro's number, for example. Let's say I gave you the grams of aspirin and I said, how many atoms of carbon do you have? Well, instead of going to using the molar mass at the last step, we would use Avogadro's number to get to the number of atoms once we had the moles, right? So if you can identify where you are in this chart, you should be able to then get anywhere, right? The hardest part is just identifying where you're at, then how you get between these numbers. Once you have your flow chart set up, then it's just a matter of using your unit conversions and making sure the units are canceling out. Right, so I think if you practice these problems, and the more you practice them, the better you get at them, using a chart like this, that'll help you kind of, if you're on an exam, you can quickly identify where you're going between, and then how to get between those. You could even look at something like this and then use which way the ratio should go, right? So if you're going in this direction, for example, from molecules to the moles of that compound, should you be dividing or multiplying by Avogadro's number, and so on and so forth. So those are some of the things we added extra. Okay. So next time we're going to start talking about using chemical reactions, right? Stoichiometry of balanced chemical equations, to then also include in these unit conversion type problems, right? So how do chemical reactions then, how can we determine how much product we're going to make, or how much we have, or how much we started with based off of using conversions and chemical quantities like these as well. All right, so we'll finish up there today. The lab might be a longish lab today, so we'll get started at like 3:20. We'll do 3:20 today. So we'll do 3:20 just 5 minutes earlier so that you guys can go ahead and get started on it.